Hi there, this is Seth Schaefer of Team Just Cause Robotics.
This video is going to be somewhat of a tutorial on how to set up the electronics for a combat robot, specifically looking at a 3-pound beetle weight robot here, but this would also apply to ant weights and also really any of the heavier bots, just with larger scale electronics that do the same thing. So here I have a pretty typical setup for a weaponed robot. So I have a weapon motor, I have 2 drive motors, I have a battery, a lithium polymer battery, which is what pretty much everyone uses. I have a radio receiver, and I have an ESC, or electronic speed controller, for the weapon motor, and 2, one for each of the drive motors, that are these guys. And then I also have a BEC, or a battery elimination circuit, which is providing 5-volt power to my receiver from the 11.1 volts nominal that the battery puts out. I also have a main power switch here, which is just a FingerTech master switch, and I turn that on with just a standard hex key. Let's talk about what all of these different components do. So, battery, everyone is familiar with the concept of a battery. It stores electrical energy and then allows you to output it into your devices to power them. In this case, this is a lithium polymer battery. Like I said, pretty much every single beetle weight robot, ant weight robot, and almost all of the larger robots use batteries similar to this. They have a very high energy density, which basically means they can store a lot of energy in a package that is both physically small and, most importantly, weighs very little. And this one has what's known as an XT60 connector on it here, and then a balance lead here. So when you're charging this battery, this is a 3-cell battery, which you can see it says 11.1 volts here. Normally it'll say, also 3S, 500 mAh, 3S, 75C. So essentially, every lithium polymer battery is composed of cells. The cells are denoted with this letter S. So a 3S pack has 3 cells. Each cell is nominally 3.7 volts, so 3 times 3.7 equals 11.1 volts. That's the voltage rating on the pack. So normally you'll see 3 numbers. In this case there's a 4th one, which is just a multiplied 2 of them together and get that, but 3 numbers that are really important. 500 milliamp hours tells you the capacity of the battery in milliamp hours, milliamp hour being 1,000th of an amp hour. So basically, this is half of an amp hour. If you were to pull 1 amp of current from this battery, in half of an hour it would die, so 30 minutes. In my case, the matches are only 3 minutes, which is about a 20th of an hour, or exactly a 20th of an hour. So this battery can supply an average current of about 10 times that half an amp, or 5 amps, for the duration of a 3-minute match. 75C means that it can discharge 75 times its capacity at once. So in other words, the maximum amount of current you can draw from this battery at one time is 75 times 0.5 amp hours in amps. So that would be 35.5 amps, I believe, or 32.5 amps. I'm very bad at mental math. Anyway, essentially, in theory, you can push that out indefinitely until the battery's dead, but realistically, they'll usually heat up and other things will start to fail if you're really drawing the full C rating of the pack continuously. So usually, you don't want to do that. On the website, this also has a burst current rating, which it can supply. And that's good because my weapon motor here, when it starts up, it can draw a peak of over 50 amps, and in fact it's rated at maximum continuous current of 55 amps, though it will never actually be drawing 55 amps continuously in my robot. Alright, let's talk about ESCs. So the BotBits ESC doesn't really have any particularly useful writing on it because it's actually just a re-flashed version of a brushless ESC. So let's just talk about a brushless ESC, which that is based on. So this is a typical brushless ESC. You'll notice the main difference between the two different ESCs I have here are the number of wires coming out. So all ESCs will have 3 sets of wires. So there's these 2 wires which go to a power source to power the ESC and the motor. There's these 2 wires that end in a radio connector or a servo connector. That's just a standard connector used for all radio control or RC electronics. That's how it is told the signal for what to actually make the motor do. And then there are these 3 wires that end in what are known as bullet connectors that go to the motor. So those are female bullet connectors. The motor has the male bullet connectors. In this case, these are 3.5 millimeter diameter bullet connectors, but you can get them in all sorts of sizes. So this ESC only really has 2 useful numbers on it. So 35A, that means that this can put out 35 amps of continuous power. Like I said before, the motor, in theory, can take up to 55 amps of continuous power, but these 2 numbers don't have to match. What really matters is that in reality, when my robot is in combat, how much current's being drawn, and if it's continuously less than 35 amps, then we're good. So I actually used a current measurement device, plugged it into my robot, powered up the weapon to full, and it drew less than 22 amps. So that's why I'm using a 35 amp ESC. However, like I said, when the motor starts up, it can draw well over 50 amps, and the amount of time it does that for is really dependent on a lot of variables that are hard to control. So in the future, I'm probably going to be moving to a 50 amp ESC, because that way, when my motor is pushing out a lot of torque and not very much speed, like when I'm trying to self-right my robot from the ground, I need to be able to sustain that 50 amps for longer, and using a 50 amp ESC is a good way to do that. So on this ESC, like I said, there's 35 amps, that's the continuous amp rating. You'll also see here something looking familiar. If I can get it to focus. 2 to 5S LiPo. That's exactly what it sounds like. It means that the lowest voltage that this will work with is from a 2-cell LiPo, which is 7.4 volts, and the highest voltage from a 5-cell LiPo, which is around 18 volts. I think 18.5 or something like that, nominally. You'll also see it says opto. That is a moniker that's used in brushless ESCs. That basically just means it doesn't have a BEC built into it. In other words, it doesn't have a battery eliminator circuit built into it. It's powered via the full battery voltage. Some ESCs have 3 wires coming out here on the servo connector instead of 2. A red wire will usually be there for indicating that 3rd wire, and that would mean that there is usually a BEC inside of that ESC, and it can supply 5 volts to the receiver, despite the fact that it can receive a battery voltage of, in this case, up to 18 volts. Basically, that means you can power your receiver from this without an external BEC. In my case, I need one, so BEC, extremely simple. It does exactly what it says. There's an arrow pointing to the right. On the right side, it produces 5 volts. On the left side, you put in whatever battery voltage up to what it's rated for, which on the website, I think this said it's rated up to 6S or around 22 volts. Really simple, this part. All that it does is make sure that you can get 5 volts to the receiver, because the receiver will not work with anything higher than probably around 6 volts. It will just blow up. So for both of my ESCs, I have to put power in, and I have to power the motors out. So the difference between the brushed and the brushless, aside from the differences of the motors that I can go into in a separate video, for the ESCs, this one only has 2 wires going to the motor through this connector here. Though it still gets 2 wires for power, because you just need, a power and then a return, or a ground, in other words, to complete a circuit. For the motor, there's 2 wires, because brushed motors are extremely simple, and you just put power in, and power comes out the other side. Brushless motors are a lot more complicated, and essentially you have 3 phases that get pulsed power, and the ESC has to time those pulses very precisely. So if you actually hook this battery directly up to one of these brushed motors, it will spin at full speed, and it won't blow up or anything. It'll just keep spinning at full speed forever until the battery dies. With one of these guys, one of the brushless motors, if you apply power to any 2 of the 3 leads, it will probably blow up that winding after it gets really hot and melts, and nothing good will come of that. You really need to be timing the power to these, and especially because when it's spinning, it's starting to spin the timing changes as it like increases its speed, so it needs to have some sort of like actual computer essentially doing that. That's really what this like that BL Heli firmware is running on a chip that's essentially just like what you'd find in like an Arduino microcontroller. Just know that generally speaking, you basically have a microcomputer in one of these ESCs, really in the brushed ones as well, even ones that aren't made out of brushless ESCs. There's a little computer handling all the pulse timing for the brushed motors to make it so that they don't just run at full speed all the time, and also allow you to change directions. Alright, let's talk briefly about the receiver. So all that this receiver does is it receives radio signals from the transmitter and then transmits them to these channels of 3 pins each. So really, there's just a ground, a 5-volt pin, and then a signal pin. It actually, I think, it might not say on this receiver, but on my other one, it literally says on it what each of the 3 wires are. So the signal wire is receiving a bunch of pulses in like fractions of a millisecond that allow it to respond very quickly to radio commands. And this is a 6-channel receiver. You can kind of ignore all that iBus sensor servo stuff. That's really only important for like a multi-copter where you have like sensors that are telling it what angle it's at and whatnot. But you can see here it says 4.0 to 8.4 volt DC. So that means that if you had a 2S battery, you could actually plug it directly into this because it would be less than that 8.4 volts at only 7.4 volts. So when it's fully charged, it's closer to 8.4, and this would still work with it. But with anything higher than 2S, which in my case I'm using 3S, and a lot of Beetles will go up to 4S or even higher, you can't plug directly into this. That's why I need the BEC. Alright, so motors. I'm using Servo City's Economy gear motors, 970 RPM variant. So here it says 970 at 12. That just means that it runs at 970 revolutions per minute at this shaft here whenever you power it with 12 volts. 11.1 volts is kind of close enough. When the battery's fully charged, it's closer to like 12.4. So at the start of a match at least, it's spinning close to 1000 RPM. And then, well, at max speed. And you can vary the speed obviously using the ESC, it's kind of the point. You can also vary the direction so that you can actually turn and go backwards and stuff. So the numbers on here aren't particularly helpful, but really the important ones are on the website. So typically you will see that there is a stall current rating, there is a stall torque rating. This is for brush motors rather. You will see usually a voltage range or maximum voltage, and you might, if you're lucky, see a like continuous power rating, maybe even a maximum efficiency RPM or maximum efficiency torque and amperage, anything like that. It could take a while to get into all of that stuff. Really what's important is, for combat robot purposes, is use what other people have used successfully in the past or something that has very similar specs. So for like a Beetle weight, the premium versions of these gear motors are very popular. These economy versions are pretty popular. The Kitbots motors that are used in the D2 kits are almost the exact same to these. So really, for me, the choice of this motor was just a matter of picking a motor that I knew people used and then picking an RPM or in other words, basically a gear ratio that was suitable for the size wheels and the kind of speed that I wanted. So since I'm using 3-inch wheels, my robot's able to get to pretty high speed but still have a decent amount of pushing power with the 970 RPM variant. I think this is the fastest variant that they sell, and the next down is like 480, so it'd be like half the speed. I didn't really want to go to that, but I know some people with like really pushy control bots use those as well. So brushless motors. It can also get kind of complicated like with brush motors if you really dig into it, and in my case for building this robot I kind of did have to dig into it. Finding a suitable motor for a given weapon setup often isn't as simple as just looking at the specs that are written, because oftentimes they're kind of inaccurate, or you have to really think about how you're using the motor to figure out if they are accurate or not. So important ones that always matter, your kV. In this case, 3000 kV. That means it spins at 3000 times the voltage in terms of RPM. So if you run this at 1 volt, it'll spin at roughly 3000 RPM. If you run it at 10 volts, it'll be about 30,000 RPM. When I'm running it at full charge, like 12.4 volts or whatever, it's going closer to 37,000 RPM. Other numbers from the website that are actually important: the current rating, or like the stall current basically for these, or peak current, it's kind of the equivalent to stall current on a brushed motor in a sense, will be the maximum that it draws on startup, and usually the current rating is pretty much the same. It'll be the maximum it draws on startup, and in theory you can run it at that current continuously without it melting, but in practice that's sometimes not the case for combat robotics specifically, because this motor is really designed to be flown in an RC airplane. So it's really meant to have a crap ton of air from like prop wash just directly blowing over it, and without that kind of crazy level of like air movement to cool it, it will get very, very hot, and it can easily like burn up in a combat bot environment. So I would not attempt to run this at a continuous 50 amps in a combat robot, because I guarantee you it will melt. It already gets almost too hot to touch running it in my robot at just half of that for 3 minutes at a time. Other numbers that are really important for this are the can size. So that's the 2836. That means the motor can is, or sometimes it refers to the electrical stator inside, but in this case the motor can very, very roughly is 28 millimeters wide by 36 millimeters long. In reality, it's pretty much never that exact size. You can look at the pages and they will tell you the dimensions, and it'll tell you exactly how large this is. So that's something to look out for. You really want to pay attention to the dimensions when you're trying to do CAD models and whatnot for your bot. The weight obviously is important for designing, but I found that generally speaking, if you're looking at like power to weight, or in other words, peak current to weight for these motors, the higher kV, you get way more power than the lower kV versions. And that just goes down to some complicated physical limitations of the electricity running through these in the coils. But essentially, when you go to a lower kV, you have more turns of thinner wire, and that means that you can dish out less current without that wire melting. This might have 12 turns of wire on each of these like green lines of the stator, whereas the version of this motor that they sell that's like 1400 kV would have to have more than double that, and that wire is considerably thinner, but because cross-sectional area is the square of the radius and not just linearly related to it, that means it can carry considerably less actual power. Last but not least, we have a switch. So really, really basic. You got to get all the specs from the website for this one, but essentially this switch can handle well over 50 amps continuously for 3 minutes, and I needed a main power switch for the bot because I don't like links, and these are really, really small and compact, way smaller in fact even than just like an XT60 connector with a second one just like plugged in as a link. And it's much easier to fit this in a bot because all you need is a little hole in the top, and then you can easily turn it on and off with a hex key. So these are used, or similar things are used in pretty much every weight class. There's ones that work for 1 pound ant weights, and there's ones that work for 150 pound heavyweights, the like Team Waiachi switches, or sorry, 220 pound heavyweights. Team Waiachi switches are used very commonly in those. Very briefly, I'd like to touch on connectors. So connectors are important. A lot of people will solder all of their wires for everything together, except for maybe like the battery, because that's the only thing that really needs to be unplugged frequently, and I generally dislike that because it makes it really hard to repair anything. You have to like cut your wires and resolder them, and the more you do that, the shorter the wires get, and it just becomes way more difficult. I know that connectors add a bit of extra weight and significant bulk, especially in the case of these XT60s, but personally I believe they're more than worthwhile to have for the time it saves you. When you're in the pits in between 2 matches, you might only have 20 minutes, and if you need to swap out an ESC and that requires cutting and resoldering 5 wires, 3 to the motor and 2 to your battery, then you're going to have a really hard time. So this is an XT60. It can carry 60 amps continuously and bursts of well over that, in excess of probably over 100 amps. This is a JST connector. It's used on a lot of the small bots. These are really cheap. You can buy them with the wires pre-wired to them. I strongly recommend doing that because crimping the little terminals onto them is a nightmare. Same goes for the RC servo connectors. you can just buy extension servo connectors with male and male ends, or male and female ends, or female and female ends. So this is the female end because the pins go into this. The male end is on the receiver. It's just 3 pins in a row. It's somewhat uncommon to see things with the male end alone, and it usually has like a shroud that goes over it. But the female ends plug into receivers, so they're pretty common on like everything really. Sometimes you'll get these multicopter ESCs with no wires attached, and then you have to like solder on your own and maybe even crimp your own connector. But I've burned up a few ESCs in my time, so I just desoldered the connectors from the ones that burn up so I can resolder them onto new ones if I end up getting any that are like that. Then we have the bullet connectors. Like I said before, these are 3.5mm bullet connectors. Pretty straightforward. They're just little barrels, and they're nice because you can rotate them to any angle. They're not very bulky. An XT60 connector is actually just 2 3.5mm bullet connectors in a housing, so you can actually directly plug like this motor into that connector if you want to, but you only get 2 wires, so that's not particularly helpful in most cases. They do make like a 3-wire versions of these that are used sometimes on electric skateboards for brushless motors, but I feel that that adds a lot of bulk and just makes your connections a bit less flexible than using these like super short little bullets by themselves. Then we have the XT30s. These are literally the exact same thing as XT60s, but really cute and tiny. These are 30 amp continuous rated, and they work the exact same way as the XT60s. Depending on what connectors you buy, you may want to tape them, you may not. I found out the hard way that taping the XT60 connectors tends to be a good idea. They're a bit looser. These XT30s takes a lot to pull them apart usually. The JSTs can vary, but usually don't take a lot of force to pull them apart, so I would recommend taping any XT60s you have, especially one that plugs into your bat before you go into a fight. And then, yeah, I think that pretty much covers everything. If you have any questions, leave a comment. And I think that in the future I will hope to make more tutorial videos like this if it's well received, so that people can get into the sport more easily and learn more about building robots.